101. This is chapter 8, which will be the final chapter for the test on next week. I will post a review tomorrow. Post a review prior to the test for that. So this is on rotational motion. Right? And this will be compared to what we've done earlier, which is a linear motion. So comparing, so we're going to have equations that are similar but slightly different because of the fact that we're going to be rotating. And this will be based on the fact that if we are in a circle, moving in a circle, we again start from the x-axis and rotate counterclockwise, right? In a full circle, there are 360 degrees. And if this is the radius r, this in terms of degrees is 360. In terms of number of radii, it's 2 pi in units of radians. And one radian is approximately 57 degrees, meaning the angular distance this way, the distance on here is the same as 1 radius. So this distance on here, so this is all angular rotation. A couple other things here we're going to be introducing are angular motion. So we've had x for distance. We are now going to be having the Greek letter theta. For velocity, which was in meters per second, this will be omega, this will be radians, this will be radians per second. And then instead of acceleration, we'll have alpha, which is units of acceleration in radians per second squared. So it'll be the number of radians. So it'll actually be an angular measurement rather than just that. Now a couple other things here. All right, let's see what else we got. So relationship between each of these is x is equal to theta times r, where r is the radius in meters. Omega, v is omega times r, and a is alpha times r. So if you have the angular acceleration times the radius in meters, you will get the actual acceleration around this circle, and this will be linear. This is not centripetal acceleration. So this will be the actual acceleration on here. All right? Again, comparing this to centripetal acceleration, which is AC is v squared over r, right? V is a constant in this case. Here, this means it's actually accelerating faster and faster and faster as it goes. So it's like a car wheel as you accelerate down the road. It's actually accelerating. A couple other things here while we're at it. Is we'll be introducing frequency, which is cycles per second. And it's units of hertz. And the reciprocal of that is period. So the period, which is in seconds, this will be in cycles per second. So there's a relationship between the period, or how long it takes to go one time around, and the frequency, which is how many times it goes around per second. So that's what else we'll be introducing. And I think that's right. That's how we're starting right now. And let's see. Oh yeah, one other thing. The relationship, so this is the angular velocity in radians per second. The frequency then is also equal to then omega over 2 pi. So this is in radians of units of radians per second. Frequency is in cycles per second. All right, so this is part of section 6.81 and 8.2. So we have the concepts here. Angular, which is measured in radians that way. Omega, which is angular velocity. And relationship to V and omega is omega times r. And then angular acceleration, which is in units of radians per second squared. And the relationship between actual acceleration and angular velocity is alpha times r. And this A is not the same as that. Again, this is where V is a constant. Okay, so I'll let you just look at that a couple more minutes. Then I'll move on to the next section here. All right. Okay. All right, let's see. Oh, yeah, we're going to be doing relationships here. So, we're going to have equations, much like we've had before. Right, so I'll leave that up. And now I'm going to leave this, but I'm going to add some examples here. So back in chapter 2, we are expressions of V is V naught plus AT, and X is V naught T plus 1/2 AT squared. And the last one, V squared is V naught squared plus 2AX. All right, where V naught is initial velocity, A is acceleration. So these are our linear ones from chapter 2. All right, now what we're going to do is look at how we use these in chapter 3, not chapter 3, chapter 8, with angular. So angular is almost the same. So instead of V, we have omega is omega naught plus alpha times t, where again, that's the actual acceleration of it. Omega, or theta, is omega naught times t plus 1/2 alpha t squared. Those are almost exactly the same, just interchangeable in that regards. And omega squared is omega naught squared plus 2 alpha theta. So those are our expressions for Okay. All right. So let's do one example here. Like this. I'm going to take this off. Right. So there's an example. Let me see here. Right. Okay, let's have a merry-go-round, and looking at it from the top, all right, we have some boy on the outside, and the radius of this thing, R is 2 meters, let's say, and a girl is on the inside at that. And what we do, this is example 8.4 in the text. What we are doing here is we'll start from rest. So omega naught is 0. And what it does is it has an angular acceleration of 0.06 radians per second squared. And it does this for a time of 8 seconds, all right? 8 seconds. Question then is, all right, determine, oh, yeah. So I want to find omega, and actually V at the outside. So the first part is find the angular velocity and then the actual velocity. Now, let me deal with the boy on the outside, and I'm going to use my expressions here. So I'll these are back from chapter 2, so I'll eliminate those, erase those for now, so I have a little more room. And we're trying to find omega. We're given omega naught, we're given alpha, we're given t. So we want to find what omega is after 8 seconds. Well, if you look at these, we want to use the first one. Omega is omega naught plus alpha t. So that'd be omega is 0 plus 0.06. I got times 8, and that would be equal to 0.48 radians per second. So it's accelerated. So what it would be is, if you look at omega and time, it accelerates at a uniform rate for 8 seconds until it reaches this, and then we turn that off and it starts going at a constant angular velocity. So your first part is to get it going faster and faster, and then we just let it go, and that's the case there. Now one question is, all right, we talked about the boy, all right, what would be the angular velocity of the girl? So this is for the boy. What would it be for the girl? All right. Well, you might think she's closer in, her angular velocity is going to be less. Well, the problem with that is this expression has nothing to do with how far she actually is out. This is actually only how fast it's rotating in degrees or radians. And it turns out this is the same for both the boy and the girl. They're both rotating together. Now so the answer is the same regardless of where you are on there, whether you're at 1 meter out or 2 meters out. So that's what the result is there. Now the question would be, what would be the linear velocity? All right, again, the linear velocity. Well, we can use our expression is omega, v is omega times t that we had just, omega times r, I should say. All right, which would be 0.48 times 2 meters, which would be 0.96 meters per second. At the end, he's going 0.96 meters per second. All right, that's for the boy. For the girl, what's going on there? Well, she has an angular velocity, but she's only 1 meter out. So her angular velocity is only going to be 0.48 times 1, or 0.48 meters per second. So he's actually going faster, actual distance-wise outside. All right, again, this is once they have gotten to this point. All right? All right, final thing here is what would be, this is alpha, and we could actually calculate from the part of angular acceleration while we're at this. Is we could look at two things. From this part here, all right, what is the angular acceleration? Well, the angular acceleration, well, is just that for the first 8 seconds. Then at t greater than 8 seconds, alpha is 0. All right? But we could look at is what is the centripetal acceleration. All right, this is, when we look at this as it's rotating, centripetal acceleration is being pulled inwards, directed inwards. The angular acceleration, this linear, is in that direction, in the direction that is actually moving. So this would be v squared over r for the centripetal acceleration. And I'll just round this to about 1 and to 0.5. So this would be 1 squared over 2, which would be 0.5 meters per second squared for the boy. And for the girl, it would be, centripetal would be v squared over r. This is for the boy. This is for the girl, and it would be 0.5 squared over 1, which would be 0.25 meters per second squared. So her centripetal acceleration is actually just half of his. So it's linear, it goes down linearly this way. Another way we could express this is we can see, so this is centripetal acceleration is v squared over r. All right, for the boy it's 1 meter per second squared over 2 meters, so he gets 0.5. For her, it's 0.5 squared over 1, 0.25. We use this relationship. V is omega squared over r. that would make that also equal to omega squared times r, which would mean the centripetal acceleration would be proportional to the radius from the center, which makes sense because at the center, if you're at the center, you're experiencing no centripetal acceleration. The farther out you are, the faster linear speed you actually have. So you go out twice as far, it would be twice as fast. So if you actually go out to 4 meters, it would be twice this, and it would be 1 meter per second squared, and so on. So this is the expression if you have omega and r for the centripetal acceleration. Again, this is different from the angular acceleration. So that's what we're going to be dealing with there, as far as that's concerned. Okay? All right. I think I'll leave it at that for this part. So this will be lecture 8A.